just a couple announcements. I'm sure you're all interested when exam 1 scores are coming out. I would expect them to come, the scores to come first, because we still have some alternate exams being taken. So I think the scores should be set and released maybe in the next 24 hours, but at the latest, I think the Thursday, with questions coming out on Thursday. I think our last alternates are tomorrow. So I won't say much, I'm not going to say much about it. I just want you to know that's the timeline, but I'll talk about the results on Thursday. And then if you haven't yet, I'm asking for feedback if you want to give it about how the class is going, how you felt going into the midterm, how you felt it went. It's like a 5-minute survey. It gives me some feedback for how, like, what to keep, what to change for the class. And then also I give personalized feedback to your recitation TAs so that we make sure that those are useful hours for you as well. Questions? Okay. Then with that, we're going to just jump right into midterm 2 content. All right? As promised, this is about chemical equilibria. So chapter 14 was this section. That's kinetics. We are now here, okay, in the green part where those concentration lines are not changing anymore. How? What? How? Why those values? Okay, that's what we're going to get at. And that really spans, so we're going to go into the basics in chapter 15. In chapter 16 and 17, we focus on acid and base systems through an equilibrium lens. And then in chapter 19, we will get into like the real theoretical underpinning of equilibrium. Okay, so this, and then in 20, we'll apply it to electrochemistry. So if you hated kinetics, and you never want to see it again, it's not going to come up until the final. But chapter 15 is one that you cannot skim over. You have to have this like as a solid underpinning for the next 4 chapters. Okay? So don't let this one slide. All right. Basically said all this already. But here's the question we're asking ourselves with equilibrium. If we give the reaction an infinite amount of time to find the perfect balance of reactants and products, what is that balance? Okay, that's the question we're asking ourselves. What's the balance? Right? So let's start with a reaction. All right, I have some N2O4. It's cold, it's over here. That's a clear substance. And as I let it warm up, some of that N2O4 is converted into NO2, which is brown. Okay, they picked this reaction because it's visually, like you can visually track it, right? At some point, my concentration of N2O4 and NO2 stop changing. That's equilibrium. At some point, this color stays the same. Okay, so let's write about that. And we're going to use just a little bit of kinetics. So when I said that you can just forget it, I really didn't mean that. That was a lie. Okay, the rate law of the forward reaction. But we're assuming an elementary step. Okay, so that means that the rate forward equals the rate constant for the forward direction times my concentration of N2O4. Okay, I'm thinking about the reaction going this way. All right. Now I want to write the rate law for the reverse reaction. And hopefully this feels sort of familiar because this is the equilibrium method that we talked about when we were doing multi-step mechanisms. Okay, now in the reverse direction, I'm going to call that rate sub R. That equals my rate constant for the reverse direction times NO2 squared because I've got 2 of them. Okay. Equilibrium is when these 2 are equal. All right, Equilibrium is when that forward rate is equal to the reverse rate. We will signal this to you in those reactions when we write it out. These are equilibrium arrows. Okay. All right. So before we set these two equal to each other so that we could redefine an intermediate, but now we're going to do something else with these. All right. First, let's visualize what's happening. Okay, we started with only N2O4. So I'm looking at the left graph here. I'm looking at time and concentration. So I start only with N2O4. That concentration starts coming down. And of course, my NO2 concentration needs to come up, right? And then I wait for the point that the concentrations don't change. So I'd say this is the time point at which we hit equilibrium. All right, so the N2O4 is coming down, NO2 is coming up. Now, the second graph shows us rate versus time. So notice that we have the blue trace is our forward rate. All right, we just wrote this on the previous slide. Okay, that's our forward rate. Okay, it starts high, and then it comes down. Why? Kf is a constant. That rate is coming down because our N2O4 concentration is coming down, right? We agree with that? And then our rate, the reverse rate, is 0 to begin with because I don't have any NO2. Right now I'm looking at my orange trace. Okay? This starts at 0 because I have none of this to begin with. But as the reaction progresses, I get more and more NO2, okay? And so the reverse rate is increasing. And eventually, what happens at equilibrium is that those two intersect, and I have equal forward and reverse rates, okay? So that dashed line, the same point where we marked here that we had hit equilibrium, we now have equilibrium here, right? Where our rates equal each other. Notice that doesn't mean that our concentrations are equal. It's the rates that are equal. I can have different amounts of reactant and product, but still be at equilibrium. Yeah? The reverse?
Yeah, like, because like the forward is like, it goes less and less because you make more like reverse, right? So does that mean that that's the product, right?
So yes, NO2 is my product. But at some point, so I think I'm getting your question, and we're gonna derive this like painfully on the next slide. At some point, right, this is also happening. So yes, I'm losing N2O4, and I think that's the way our mind is programmed when I write the reaction like this. You look at it and you say, oh, okay, N2O4, that is my reactant. It is converting to NO2, but what I'm saying is at equilibrium, NO2 is also going back and refilling my N2O4 bucket. Both are happening, all right? So now we can do some derivations here and understand what we're going to call the equilibrium constant. All right, so we're assuming equilibrium. And when I say that, we're gonna begin with our forward rate equaling our reverse rate. All right, so I'm going to write that out. That Kf times N2O4 equals Kr times NO2 squared. All right, so at equilibrium, those concentrations are constant. What can we take from the graph over here? All right, at equilibrium, we have more NO2 than N2O4. Right? We all agree with that? the end of the day, when this has reached equilibrium, I have more of my product than of my reactant. So what does that say about this? The equation we just drew. This number is bigger, right? So then this number is smaller. Okay, we pulled that off the graph. So that also tells us something about the relative size of Kf and Kr, right? If I know that those two things are equal to each other, but I've already told you that the concentration of NO2 is bigger, then I must know that Kr is a smaller rate constant. And Kf is the bigger rate constant. Right? So if I have those, if those two are going to be equivalent, and I read off of this graph that I have more NO2 than N2O4, that tells me something about the relative size of Kf and Kr. Okay? So Kf is bigger than Kr. All right, we're going to take this one more step. So from this equilibrium equation that I've written here, I am now going to solve out for a new constant. Okay? And it was not my decision to also use K for this. I wasn't there, but we're going to use capital K for the equilibrium constant. And I really struggle to make my big K's look different than little K's. Okay, but that is a big K. Big K. And that's equilibrium. All right, so I'm going to take my equation up here, and I'm going to separate my rate constants from my concentrations. Okay, I'm going to bring them to the same side. So I divide both sides by Kr. I've got that big K equals Kf divided by Kr. That it depends on the relative size of the forward rate constant versus the reverse rate constant. Or I could put it in terms of concentrations. I could say that my equilibrium equals NO2 squared divided by the concentration of N2O4. Okay? Those two are going to be equal. Those concentrations in that have to be equilibrium concentrations. They can't just be at any random time point. I have to be in this part of the graph when they're not changing anymore. That's what makes it special, is because I am at equilibrium. All right? So we know from this now, I already told you that NO2, we looked at it, we said that it was greater than N2O4. So in this case, big K would be greater than 1, right? Because I have more NO2 than N2O4. All right? For the rest of the chapter, we are primarily going to make these, make analysis and assessment off of the concentrations. But I want to point out something we can learn from this part right here, from the rate constants. Okay, so we're going to take this and we're going to bring it down and do some math. Big K equals the forward rate constant. And now I'm going to remind you, hopefully this hasn't gone away, that a rate constant equals, per Arrhenius's equation, A times E to the negative EA divided by RT. Okay? So I'm going to put that in. I'm going to put those definitions in for my rate constants. That A times E to the negative EA. And now I'm going to specify that this is the forward activation energy divided by A E to the negative EA divided by the reverse activation energy. And I've made an assumption here. My assumption is that A, that frequency factor, has not changed. Okay, so that cancels. So this is going to drop. I'm going to use some exponent rules, that EA divided by EB equals e to the a minus b. So that's what I want to do with these exponents. I'm going to have e, all right. Now I'm going to have EA reverse minus EA forward divided by RT. And this is the point that I wanted to get to, was that now if we look at a reaction diagram, stay with me. This is a reaction diagram showing me an EA forward and an EA reverse. Okay? If I take EA reverse and minus EAF, does anybody recognize what that energy difference is? That's the energy difference between my reactants and products. This distance minus that distance, that energy, gives me delta E. So whether or not this is an exo or endothermic process is going to really dictate the size of K. Before we didn't care about it. We just said, hey, when we were doing kinetics, how fast can I get over this barrier? Now the thing that determines big K is delta E. That's going to be the primary feature, that E to the delta E divided by RT. Oh, and I think I minus, plus, minus, okay. Yeah.
I'm confused by the numerator and denominator. I thought it was A minus B. Wouldn't
Yes.
it be the top term minus the bottom term?
So yes, because I have negative EAF minus a negative EAR.
Thank you.
Does that got it? Okay. And I think this winds up the way that I end up defining it. That's got to have a negative in front of it. So that the delta, negative delta E, that's what we're going to have up there. But the point that I want to make to you guys, sorry for the hand waving there, is that that distance is the one that we're interested in. Does that make sense? Yeah.
Did you say A minus B, like the exponent rule? Did you do reverse minus forward? Wouldn't it be forward minus?
Well, I had a negative down here, so it's negative EAF minus a negative EAR, and so that makes the second term positive. See, does that make sense? And so I flipped it. Yeah. Okay. The point that I want to make is that the equilibrium constant depends on delta E. Is it landing? Okay. All right. So generically, when I have this equation, the equilibrium constant is given by the equation. So Kc, this is our new big equilibrium constant, equals, all right, and again, we don't often think about it as rate constant over a rate constant. We're going to think about it as concentrations because that's what we'll measure when we're in the lab. So very loosely, it's products over reactants. Okay, I just keep that phrase in my head when I need to decide how I'm going to write this out. But I'm going to have the concentration of D raised to D, E raised to E, over A to the A, and B to the B, where these are the coefficients. Okay? And again, what's really important is that you don't pick random concentrations. These must be equilibrium concentrations. So it can't be before, like while the reaction is still going. I can't pull random time points. I have to wait until they're constant. That's what's special about it. All right. So things that I want you to know about equilibrium. This is like the conceptual stuff. Systems, we don't have to do anything. Systems will spontaneously make it to this point. This is where they naturally gravitate to. All right, I don't have to do anything. They make it there on their own. It might just take billions of years, but I don't have to intervene, okay? Equilibrium is dynamic, okay? It doesn't mean that the reaction is stopped. It just means that our forward rate and reverse rate are equal. Okay, so don't let it be a static thing in your head where the reaction has stopped. It's that forward and reverse are the same speed, okay? All right, for equilibrium to occur, this is important, we can't let in more reactants or let them out or let out products. We have to close the system. If we don't close the system, we won't reach equilibrium, okay? So it's got to be closed. And then at equilibrium, we've got this big K, okay, which can be represented by rate constants from kinetic trials, or this ratio of constant concentration terms, which I like shorthand to products over reactants. It's just a reminder of what I'm looking at. All right? So read through these statements, right? This would be like a conceptual style question on your next exam. Identify which ones are true and which ones are false. Oh, geez. Okay, talk to a person next to you. Make sure that you guys have agreed on what the true or false statement is. Okay? There's only one true statement. Give me a thumbs up when you have come to your conclusion. All right. Hold up the number that you think is true. 1, 2, 3, or 4. Good. Seeing lots of 2s. 2 is the correct answer. All right. So at equilibrium, all right, we're looking at an A to B reaction, all right? Which of the following statements about the equilibrium is or are true? At equilibrium, the concentrations of A and B in the reaction mixture must be equal. That's not true, okay? If they have a very big, if they're very different in their energies, if there's a large delta E, then they are definitely not going to be the same because one is favored more than the other, all right? The only time that would be true is if they had the same potential energy, okay? If there was no change in enthalpy and technically entropy, okay? But this is not a given. It is not a must, okay? So this is false. There is a scenario when that would be true, but it is not always true, okay? At equilibrium, the processes A to B and B to A have the same reaction rates. That's the true statement, okay? That the forward and the reverse rate are the same. All right, the next statement is very similar to the first one, where I say at equilibrium, the processes of A to B and B to A have to have the same rate constant. That is like saying the first statement. If they had the same rate constant, then their concentrations would have to be the same. Okay, but that's not a requisite, and it usually isn't true. Okay, so that's false. That's not a necessity. And then lastly, at equilibrium, molecules of A are no longer converted into molecules of B. Again, that would paint a static picture that this has stopped. That's not what equilibrium is. Equilibrium is dynamic. It's constantly moving back and forth. It's just we're at the same rate. So that is also false. All right? That would be a conceptual style question that you could get on the exam. All right. Or we could give you a quantitative question. This is the easiest type of quantitative question that you might see on the next exam, in my opinion at least. All right, you get this reaction. All right, and then you would be able to use that to write our Kc, the equilibrium constant. And then I'd say, hey, at equilibrium, I know what the concentrations of NO2 and N2O4 are. Can you tell me what the equilibrium constant is? Yes, you can, because you can just plug those numbers into this equation. So I'd have Kc equal to 0.03101. And I'm going to talk about why I just erase that m in a second. Divided by 0.00452. All right, so I get a Kc value of 0.212. And notice that I am not writing units, right? That's not a mistake. That's because our equilibrium constants, we don't write them with units. They are unitless. Okay, so let's put a little note here that this is unitless. And you're like, well, how can it be unitless? I have m squared over m. That should be m, okay? Well, we're doing some behind the scenes math. So the reason behind this is that we're actually taking the activities and you really just need to believe me that we don't report units, but I'm telling you the why. So we're taking the activities, and an activity means that we're dividing the concentration by 1 molar. So all of the concentrations are by 1 molar, which effectively drops all of the concentration units and leaves us with just the number. So there's no units, but we just say, hey, we're going to put in concentrations, because numerically that's what we're doing, but we drop the units, okay? This is true. We're also going to look at doing this for gases, so we'll have a Kp. So when we have a pressure, for a gas, we're taking, we're taking it by 1 atmosphere. So again, we just drop out the units and leave it as a numerical value, which is why I can then report that Kc is equal to 0.212, period, not 0.212 molar. All right? And that's like, this will also help us when we look at solids and liquids, but for now, I just need you to believe me that you don't need to report units for Ks. All right? So do the second part here. So this is the other easy type of question. that you might see the Kc, I give that to you, and then I give you one of the equilibrium concentrations and ask for the other one. So just make sure you set that up. And I will point out that on the exam, there will be times when we don't tell you this. All right? That when we say we haven't given you an equilibrium value. This is a really easy question because we tell you it's at equilibrium. So make sure when you're reading through the problems, you need to say to yourself, are they giving me an equilibrium value or just some random time point? We can deal with the random time points, but that's going to be a harder question. So again, we're just plugging numbers in here. All right, now I have a known concentration for that NO2, and I'm going to solve out for N2O4. All right, so I find that my concentration of N2O4 for this problem, no, we've decided that's permanent? Okay. N2O4 equals, what did I get for this one? Did you guys get 0.0474? And that is in molar. Okay. Yes? Okay. The key reading piece here to make this a simple problem is that I tell you it's equilibrium. Okay? All right. Now, again, I just alluded to this. We can also deal with Kp. All right? That is for gas phase reactions where instead of putting it in concentration units of molarity, I have it in pressure units of atmosphere, all right? So again, we're looking at the same standard reaction here. So the way I would write this is instead of using concentrations, I'm going to use partial pressures for all of my products and all of my reactants. Those are still raised to the same coefficients, okay? The thing that I need you to understand is how do we relate Kp to Kc, all right? So we got to do a little bit of math here for that. And we have to bring back the ideal gas law. So I'm going to redefine each of these pressures. All right, so remember that PV equals nRT, right? So PD, I'm now going to specify this for the species D. PD equals the number of moles of D times RT over V. All right? Now, I will notice that the moles of D over the volume, that's concentration. So I could write that as the concentration of D, right? Number of moles divided by volume. That's molarity. That's my concentration. All right, I could do that for every single one. I could say, all right, for D, E, A, and B, those pressures equal the concentration times RT. So I'm going to plug this in to my Kp expression. So Kp will now equal the concentration of D times RT raised to the D. Okay, and I'm going to do that for each species. All right. Now, we have some familiar terms here. So what I can do is rearrange this and say Kp equals, I notice that I have all of my concentrations in here. So I could rewrite this as D to the D. I'm going to pull, basically what I'm doing is I'm pulling out my RT terms. And I'm going to set them off to the side. Because what I want to be apparent is that within this, I have Kc. Okay? So this, I've just written Kc, right? But I need to multiply it by RT, and this is to the D, RT to the E, divided by RT to the A, RT to the B. And I can consolidate this. And that's what's going to make this a lot easier. Is if we look at this term, and I'll switch colors here just to emphasize. This equals RT to the D plus E minus A plus B. All right, so again, I'm just using some exponent rules. And what that is, D plus E is the number of moles of my of my product in the gas phase. And A plus B is the number of moles in the gas phase on the reactant side. So how this will be shown to you, and you guys get this equation on your exam sheet, is that this equals RT to the delta N. All right, and that's going to be our final version, is that KP equals KC times RT to the delta N, where delta N is the change in gas phase moles. And we'll look at an example on the next slide. All right? So to make this conversion, all we needed to recognize is that partial pressures depend on the moles. I can see those moles over liters as a concentration. And so I pull Kc out, and I'm left with this RT to the delta N. All right, so what kind of question might you see like this on the exam? You might see just a straightforward conversion, okay? Hey, Kc for this reaction is 245 at 1,000 Kelvin. What is Kp? All right, so using that equation on the last sheet, answer this question, where delta N equals moles of product, and this has got to be in the gas phase. This is one term, minus moles of product in, and by product I mean reactant, in the gas phase. All right? The next question you're probably asking yourself is, what R should I be using? Right? We wrote that Kp equals Kc times RT to the delta N. On your equation sheet, you have two different R's. One of them is the 8.314. That's joules per mole Kelvin. The other one is 0.0821 atmosphere liter per mole Kelvin. Since this was all about converting from pressures to concentrations, you're going to pull the R that has atmosphere in it. So this should be the 0.0821. Okay, so plug those numbers in, make sure you're getting the right answer, and then cross-check with somebody next to you. Okay? right, let's plug these in together. So you get this question, Kp equals 245 times, and I'm just going to plug numbers in, all right? I'm dropping units, and then to the delta N. This is where I think I normally have it the other direction, and you get a positive number. In this case, you should have gotten a negative number. I took 3 moles, okay, on the gas, on the reactant side. I had 2 and 1, and I turned them into just 2. So my delta N should be 2 minus 3, or negative 1. It is fine for that number to be negative, okay? So I'm going to raise this 0.0821 times 1,000 to the negative 1. That gives me a final answer of 2.98. All right? Hold this in your head, when will Kp and Kc be the same number? Okay? If delta N were 0, if there is no change in the number of moles on the reactant and product side, then I'm raising RT to the 0, which would be 1. So Kp would equal Kc when delta N is 0. Okay? And in this case, it did not cross your mind not to count any of those because they were all in the gas phase. But we are going to see reactions where you have stuff in the solid phase or the liquid or aqueous, and you don't count those. Only count the moles that are in the gas phase. So don't ignore what's in the parentheses. Delta N is only from gas phase. All right? So what can we do with these equilibrium constants? All right, why are they useful to us? Again, chapter 14 was how fast things went. That's a practical question. How can we speed it up or slow it down? Again, there is practicality in understanding equilibrium constants. All right, we want to know, hey, we want to make this product, but the equilibrium tells us that we won't make very much of it. So what can we do? What levers do we have to make more of the thing that we want? All right? So we want to maximize productivity. So at the end of this, we'll talk a lot about the Haber-Bosch process, which is how we make industrial ammonia, which is really important. Fertilizer source, it's like why all of us are here. We can't make enough food without it. I think it's something like 50% of the nitrogen atoms in you have gone through industrial Haber-Bosch processes. I'll continue to yell at you about it because it's pretty fascinating. But we want to know how to make more of something, okay? So very basically, what do we learn from the value of K? All right, so if K were equal to 1, and we have a balance or equal amounts of product and reactants. All right, this is the first step here. I just need you to start seeing big K values and translating that into like, what does that mean about how much of product and reactant do I have? If K is really big, if it's a lot bigger than 1, I have more products than reactants. All right? If K were less than 1, right, then that would mean to be less than 1, I had more reactants than products. That denominator would need to be bigger, all right? So if I found I had a really useful reaction, but the equilibrium was very small, it really favored reactants, I'd need to figure out how to push it forward, how to make more products, all right? I have 2 visual analogies for you. So my first is that I visualize these reactions as seesaws. So if you have your seesaw, this is like what's standard, right? They put the balance point in the middle, right? So if you put the balance point in the middle, that would be like K is equal to 1, which means to balance this seesaw, I need equal amounts on both sides, right? Does that follow? You all have played on seesaws before? No? Well, they're pretty dangerous. I fell off of one and then was not allowed to be on one anymore when I was a child. But they make them safe now, kind of. My kids go on them. It's dangerous. All right, so this is, if you don't like this doesn't resonate with you, I have another analogy coming up, all right? But when I say, okay, this is k equals 1, we have a balance, equal amounts. If I find that I have a very small k, that means that my balance point has shifted. To balance a teeter-totter like this, I need more reactants than products. Okay, that would be me finding equilibrium for something like this, where to find balance, I have to have more reactants than products. The same is true if k is a very large number. It shifts over towards the product side, and to balance this, I need more product than reactant. Okay, that position, the position of the pivot point here, technically the fulcrum if you take physics, okay, that k, that's a fundamental feature of the reaction as written. And that's what chapter 19 is about. We will get into why that k. But now we just need to be able to deal with k. All right? So I've got another practice problem for you. Write the expression for Kc for this gas phase reaction where carbon monoxide reacts with Cl2 to make phosgene, COCl2. And then if that Kc, if I give you the Kc value there, at equilibrium, what do I have more of? My reactants or products? All right, we all have an equilibrium expression. This is like going to be, it's like the entry-level question on the exam, okay? This is going to be fundamental to so many questions on the next exam. You have to write the right Kc expression. All right, this one's straightforward. There's no coefficients. There's nothing funky about the phases. This is just Kc equals the concentration of COCl2 divided by CO divided by Cl2. All right, I see that Kc is a very large number, times 10 to the 9th. That must mean that at equilibrium, I have a ton of COCl2, right? Okay, that's interpreting that. Here is the other visual that I like to use for equilibrium, all right? On the axis here, I have on the left all the way over here, this is 100% reactants, okay? K would be essentially 0, a tiny, tiny number. In the middle, we have the 50-50 mix. On the far right, we have an infinite K, 100% reactants. I'm going to draw this for the reaction we just looked at, where we have a K that's very big. The K is the low point, okay? That's K where I draw my low point. All right? That's the low point. And then as I go up in either direction, as I go right and left, the hill goes up. All right? Why do I draw it like this? Because if I were to then put a ball, if I were to start this reaction with 100% reactants, it would not stay there. It's not at equilibrium. It would spontaneously roll down to that low point, okay? So it doesn't matter where you start, what combination of reactants and products you start with. Anywhere, even I could start here. So like this is very obvious. I start here, this comes down, right? 100% reactants. Well, I have a big K, so I should make a bunch of product. But this would be even true. If I started with 100% of the product, I would still roll back down a little bit. Because even though it's a big K, there is still a very tiny amount of reactant in there, right? So that K tells you the low point, where the system is going to gravitate to. And it doesn't matter what mixture you start with, the ball will always roll to the low point, okay? Doesn't matter where you start. You always go to that point, all right? All right, a note on notation and language, fun sides. Okay, we did this. This was the first thing that we did, okay, this N2O4 to 2NO2. All right, we wrote this, we wrote that calculation. We said, hey, Kc is 0.21 or 0.212. So now, can we say that the equilibrium constant for NO2 and N2O4 is 0.212? And the answer is no, not exactly. I can say that Kc is 0.21 for just this specific reaction as written, okay? So let's consider. I could look at the same reaction, but I could reverse it, all right? So now what if I'm thinking about 2NO2 going to N2O4? What would Kc be for that? Okay, if I wrote out Kc, I would now have N2O4 on the top and NO2 squared on the bottom. When I calculate that number is 0. And by 0, I mean 4.72. All right, that might not seem significant, but that is equal to 1 over 0.21. In other words, the reciprocal of the forward reaction. So when I flip the direction of my reaction, my equilibrium constant is the inverse, or the reciprocal, okay? So K, I might write this as K forward, and that's big K, equals 1 over K reverse, right? So that 0.212 was only for when I wrote the reaction in that original direction. All right? I can do other things to this reaction, right? I can reverse it, or I could multiply through by a constant, right? I could say, hey, actually I want to have 2. Oh, and I flipped that one there. So we're going to read it. I flipped it here. Don't look at this one. I just have multiplied through. I've taken this and multiplied by 2. All right, so what is my new Kc for that? I'm going to have NO2 to the 4th divided by N2O4 squared. And what I can recognize in that is if I were to write NO2 squared divided by N2O4, okay, and then square that, those two are equivalent. And the reason I did that was because I wanted to show you that that is our old K value, right? That is for the original reaction before I multiplied by 2. So I have this new relationship where I say, okay, K new. If I multiply by a constant, I'm going to take my old equilibrium and raise it to that coefficient. In this case, it was a 2. Right? So my K old squared is my new Kc, because I multiplied through by 2. All right? And I promise there's a point to doing this, so stick with me. It's not just to torture you. Okay? We have one more rule. Okay? We reversed it. We multiplied by a constant. The last thing we might want to do is take 2 reactions and add them together. All right? I want you to try and figure out the relationship for this on your own. Okay, take, let's say, 2 minutes. Write out Kc1 and then Kc2. Write out the net reaction, and then write what the K total is for this new reaction. What is K for the new reaction? And then I want you to put that in terms of Kc1 and Kc2. All right? So you're going to start here. Write these. okay? Okay, give me a thumbs up. Have you got KC1 and KC2 down? Okay. Have you written the total reaction, the net reaction? Is that where we're at? Okay, write the net reaction. You could even ask yourself, if this were a two-step mechanism, what would the intermediate have been? What is canceling out? Okay. All right, and then once you have that net, I'm going to start writing out my KC1s and KC2s. You keep working on the net reaction. All right, there's my net reaction. Okay, Br2 has dropped out. Okay, so I go to write K total for this reaction. I say, okay, I've got NO squared times BrCl squared divided by Cl2 times NOBr squared. And my challenge to you was to say, hey, how does K total relate to K1 and K2? Give me a thumbs up if you see the relationship. Okay? What I notice is that when I add together two reactions, okay, I will get a new equilibrium constant that is the product of the two individual reactions. So my new K total is K1, Jesus, times K2. My mind is not plugged in today. All right, so why? Why does that make sense? Well, if I take K1 times K2, the thing, my Br2 that was a product before, is now a reactant. And so when I bring those two together, they cancel. And I'm left with my net reaction. Yes? Okay, you've got 3 rules. Okay, we just did them. Our first rule, reverse the direction of the reaction, take the reciprocal of the equilibrium constant. Multiply through by a coefficient. My new K is the old K raised to that coefficient. Add 2 reactions together, and my new K is the product of those Ks, okay, of each step. And so now, the question is, why would anybody want to do any of these steps? What is the point of doing this? And there is one. It's useful, okay? Let's say, all right, this is our practice problem. Let's say I want to know, I haven't done this bottom reaction before, where I take HF and I react it with C2O4, And I added that too because I noticed I had a charge imbalance, but you guys don't have that. So that was for me. It doesn't really matter for you guys. All right. I want to know what will be the equilibrium for this reaction, but I haven't done it yet. But people have done these other two reactions. Okay? If I know the equilibrium constants for those top two reactions, I don't even need to go into the lab to figure out equilibrium. I can predict the equilibrium using those three rules and those two reactions. I'm sure you're like, wow, that's incredible. This is the best day ever. All right, so when you get a question like this, what do? I want to know this, and I need to put it in terms of two equilibrium constants I already know. So I have to figure out, how do those two reactions, how can I use them to make the final reaction? So what I would notice here first is that, hey, on my reactant side, I have two HFs. Okay? In the reaction up here, I only have one HF. So I think I probably need to multiply through by 2. Right? So I really want 2, 2, and 2. Right? I'm going to multiply through by 2 there. Because in my final reaction, I need 2 HFs. The only way I'm going to do that is if I multiply through by 2. So now, I don't just have KC1 there. This, once I multiply through by 2, is now KC1, that's squared. Right? Okay, my next step, what do I notice next? Hey, I've got this, oh, and there should be a 2 there too. I've got this anion, this oxalate, on the reactant side, but in the provided reaction, it's a product. I better flip that, because I have to have the C2O4 2- on the left side. So let's flip the second equation. Okay, so I'm going to flip this. I'm going to reverse it. All right, and so then I would have 1 over KC2, right, if I reverse it. And then I'd go through and I'd check that I had actually made the reaction that I wanted. So I'd have 2HF plus 2H plus C2O4 2-, because I've reversed the second reaction. That goes to H2C2O4 plus 2H plus 2F minus. I notice that I've got 2H pluses on both sides. Those cancel. And yes, I have just recreated the reaction that I'm interested in by adding those two together. So I use my third rule. What do you do when you add two together? You take the product. So KC, for the new reaction, I'll call that total, equals KC1 squared times 1 over KC2. You can think of these as fun little puzzles. This is the end thing I have. These are the pieces I have. How do I arrange them, resize them so that they add up to be the thing that I want? And then you do some fun math along with it. Okay? When I put these numbers in, I got a value. There it is. I got 0.122. Okay? So without even going into the lab, if I just knew some background information, I could predict the reaction's equilibrium constant. That's nice. That's cool. That's good work for a chemist. Okay? And I see that it slightly favors the reactants because it's a little bit less than 1. All right? So, you guys will, let's see, I definitely have given you guys one of these questions on your recitation for this Friday. So you'll see some practice, and then there's some in your homeworks as well. All right. Let's hit heterogeneous equilibria for the last little bit of class. We have been simplifying. I have been very intentional to only pick homogeneous equilibria. Basically, every single thing, okay, every reaction has been all in the gas phase or it's been all aqueous. Okay? Of course, that is very limiting to the actual chemistry that happens. So heterogeneous equilibria is when we have reactants and products that are in different phases. Okay? So let's consider one that we've already looked at. Okay? For example, above their saturation point, solid salts exist in equilibrium with the saturated solution. All right? This is what we looked at in chapter 13. Okay? This is chapter 13. But now we're going to look at it through the lens of an equilibrium constant. Okay? All right, remember, we said, okay, I can put in some NaCl. It will dissolve. I put in some more. And then it will dissolve. But eventually you hit a saturation point. Beyond that saturation point, we have a dynamic equilibrium. Okay? The dynamic equilibrium meaning that we have some solid, some of that is dissolving, but simultaneously, some of it is recrystallizing. And so ultimately, we have an equal forward rate and an equal reverse rate. Okay? So this is a dynamic equilibrium. And we should be able to talk about it with a K. All right? We notice that as we continue adding in more solid, if I put in more NaCl after hitting saturation, the concentration does not go up, right? That should hopefully feel comfy. So then the question is, here's our, we've got NaCl solid, and some of it is dissolving, going to Na plus and Cl minus. All right? And then some of the Na plus and Cl minus is going back to the solid. So I want you to write a Kc for this. How would you write a Kc? Then I want you to look, just in you might feel it, I am leading you down to an incorrect answer first. So then I want you to look at the terms that you just put into that Kc and ask yourself, one of them in particular might feel illogical. Like, what does it mean? Hopefully one of them will stand out to you as like, I don't know how I would calculate that. Okay, so as we've learned it so far, you probably would have the inclination, hopefully, to write this. And this is the term I want you to feel uncomfortable with, okay? What is the concentration of a solid? It's 100% itself, right? There's no, if I make it bigger, if I add more of it, the volume goes up. The concentration is always the same. It is doesn't make any logical sense to talk about the concentration of a solid. Okay, so what we'd really say is that the activity, remember I brought up this word activity before, activity of a solid or liquid is 1. Okay, and so the rule we come to is that in these expressions, we never include the solid or the liquid. So in K expressions, you don't write a solid or a liquid, okay? The other reason, the place that I find comfort with this is that, hey, I think because you have some intuition for this, and we just talked about it in chapter 13, okay? Here's two different solutions. They're the same volume. In one of them, I have a lot of NaCl. In the other, I have a very tiny amount of NaCl. Right? Both of these are at equilibrium because I have some solid sitting at the bottom. I'm past saturation. But the concentrations are the same. Okay? So I should have the same equilibrium expression for both of these, even though there's different amounts of NaCl solid at the bottom. As long as there's some there, I am at equilibrium, but I don't care how much because The activity of a solid is 1, so mathematically it drops out. All right, so here's your rule, the hard thing. If you have zoned out and you're not listening anymore, come back and listen to this statement. When writing heterogeneous equilibria expressions, we do not include the solid or the liquid phases. Those things do not show up in the expressions. We have two sort of justifications. One, the concentration of pure solids and pure liquids are constant. They are 100% themselves. The concept of concentration doesn't even really land for them. All right? If we increase the mass, we increase the volume. It's just like it's always the same. And then the really technical way of thinking about it is this activity concept. The activity of pure substances is 1. And so it just doesn't have an impact on doesn't actually have an impact on K. So we go back to this, and Kc for this is just Na plus times Cl minus. Of course, for me to be at equilibrium in the first place, there has to be some NaCl solid at the bottom. I just don't care how much, but it's got to be there for the chemistry to work out. Otherwise, it's unsaturated, and all of it's dissolved, and it's not a dynamic equilibrium. Okay? So, write an equilibrium constant expression for this heterogeneous equilibria. And you're not going to do anything different. But who are you not going to include? Water is not going to get a seat at the table. I need it there. All of this is aqueous, but there's just so much of it that I can't think about the concentration of H2O really. Okay, that's what I'd be looking for. Okay, so just, again, I often, even myself, skip over the phases. Don't do that. Don't skip over them. You'll get the question wrong. Okay? All right. This will be our last thing for today. All right? So I want you, let me set up this bell jar for you. All right? In this bell jar, I have some calcium carbonate, and I have some calcium oxide, and above that is some CO2. All right? They are in equilibrium according to that reaction. So what is Kc for this reaction? Okay? Where does the system naturally gravitate to? What dictates that? Okay? This is a really simple Kc expression because we don't include the solids. It is just the concentration, or if it was a Kp, the pressure of CO2. That's the only thing that dictates this equilibrium. All right? So let's go through a couple changes. What if some, okay, so I'm sitting here, I've got this bell jar. I haven't done it, I magically swoop in there without letting any of the CO2 out or any more air in. I magically swoop in and I take some of the CaCO3 out. Does my system have to change? Does something about equilibrium change? Okay, I pull some of the reactant out. As long as there is still some calcium carbonate in there, that is the important part where I say that some but not all is removed, there will be no change to the system. The whole time, okay? I'm going to write it stayed, the system stayed at equilibrium the whole time because my pressure of CO2 did not change. Now the next question, what if the vessel was opened? Okay, I had maybe a port and I could untwist it and let a little bit of that CO2 out. What would change? Okay? Then, in this case, to start, KC, the system would not be at equilibrium. So I said to start, okay? Once CO2 is released, the system is no longer at equilibrium. But remember, I said that systems spontaneously go back to equilibrium, okay? Without me doing anything. So as soon as I take some CO2 out, the system is like, no. I don't want to be here anymore. I want to be back at equilibrium. So when I take CO2 out, some of that calcium carbonate reacts to make more CO2 and calcium oxide. Okay. But as long as I don't mess with the CO2 amount, then the system is happy. Okay? All right, we'll leave it there and we'll come back and we'll review and then dive even further into equilibria.